Hey there, welcome back to this video. This is 4-4 curve sketching, and this is the last example for these curve sketching. Okay, so let's go ahead and get right to it. Here is example 3. And the first thing we want to analyze with these functions is the domain. Are there any domain restrictions? Now, again, this is a radical function. Radical, right? I have a square root in the denominator. Okay, so that makes it radical. Again, we don't want those values to be less than 0. That would produce imaginary outputs. And notice my radicand is squared plus 2. So no matter what I plug in there, I'm not going to have any values that are less than 0. And then also too, this is also a rational function. We have values, right? If our denominator is 0, then those values will create an undefined value. So we don't want our denominator to be equal to 0. However, again, I have an x squared term plus 2, so that's never going to be equal to 0. So our domain is all real numbers. Negative infinity to infinity. Okay, and if I don't have any worries about the denominator being 0, then I don't have a vertical asymptote, no restricted values. Okay, and this doesn't reduce, so I don't have any holes. The numerator is just x, so when I set this function equal to 0 and I clear the denominator, we get x is equal to 0. So we're going to have an intercept at 0, which will also be our y-intercept. Okay, and then now we'll look at end behavior. Now, end behavior, remember with radical functions, hey Maestas, with radical functions, you have to worry about a plus and a minus horizontal asymptote. Okay, so if I go ahead and what I'm going to do is I'm going to look at this function. In the numerator, we have x, the denominator, a square root of an x squared. This kind of gets treated as an absolute value of x. So we have a linear over linear, same over same, and we're going to take the ratio. So that's going to be 1. So plus or minus 1. The question is, where is it going to be positive and where is it going to be negative? Well, we're going to have to do some sign analysis. So the limit of f of x as x approaches negative infinity. Now, if I plug in negative infinity, okay, or just a really, really large negative number, something like negative 2,706,000, okay, if I plug that in, I get a negative in the numerator and a positive in the denominator, okay, so that is negative. So that's negative 1. And then I'll do the same with a positive value. So if I plug in, I don't know, let's just pick any positive number, right? A really large number. Okay, I'll get a positive number on top, and then the denominator also positive, so this would be positive 1. Okay, so there's my end behavior. Symmetry, linear function, this is odd, and the denominator is an even function. So an odd divided by an even, this is going to be an odd function, so we have origin symmetry. Okay, and then we'll go ahead and look at our f prime and f double prime to get increasing, decreasing, and concavity. Okay, so if I look at f prime of x, so here's f prime. Notice the numerator is just 2. So it's not possible to have 2 be equal to 0, so I don't have a critical number there. And then we don't have any undefined values for this function, so there's no critical numbers. Okay, well, is my function always increasing or is it always decreasing? That's what we want to investigate then. Okay, so this is strictly monotonic. Okay, and is it always increasing or decreasing? Well, we can just plug in any value and then we can see, okay, is it positive or negative? So numerator will always be positive. If I plug in, I'm just going to pick 0. So 0 plus 2, that's a positive 2 cubic root. Okay, cubed, then the square root, that's positive. Okay, so this is always increasing, this function. Next, we'll go ahead, and if it's always increasing, what does that mean for maxes and mins? Well, it means we don't have any. None. No relative maxes or mins. Okay, so then we'll go ahead and we'll look at f double prime. And when I analyze the zeros, we get negative 6x equals 0, which tells us that x is equal to 0. Critical number there. And then are there any undefined values? Again, no, denominator can't ever be 0. So we don't have any undefined values there. Okay, so I have a critical value, and I'm just going to go ahead and test on either side to see, okay, what's going on. If I plug in -1, okay, I get a positive on top, and in the denominator, we get a positive, okay? So it's concave up, left of 0, and when I plug in +1, we get a negative over a positive, so that's concave down. Okay, so point of inflection, 0, and the output is 0, right? We knew that that's an intercept. Okay, so here's our graph. I have all real numbers. I have an x and a y-intercept at the origin. We have n behaviors that go to +1 when x approaches positive infinity. At negative infinity, our function approaches -1. And 0, 0 is an inflection point. Okay, so I'm always increasing. So I'll start out here, always increasing. And this is concave up. Concave up. So here. Okay, and then I'm going to change. And there we go. Concave down. Okay. All right, there's our function. Our radical function, dude. Tubular. All right, thanks for watching. That is it for 4-4 curve sketching. Catch you next time.